So let's get started. So welcome to another exciting lecture about security and why the world is so terrible. So today we're going to talk about private browsing modes. Okay, something that a lot of you probably have a lot of personal experience with. So at a high level, what is the goal of privacy? When security researchers talk about privacy, what are they talking about? Well, at a high level, they're talking about the following goal. So any particular user should be indistinguishable from a bunch of other users. And in particular, the activity of a given user should be sort of non-incriminating when viewed in light of activity from a bunch of other different users. And so, as I mentioned, today we're going to talk about privacy in the specific context of private web browsing. And so there's actually no formal definition for what private web browsing means, and there's a couple different reasons for that. So one reason is that web applications are very, very complicated, and they're adding sort of new features all the time, like audio and video capabilities and things like this. So as a result, there's sort of this moving target in terms of what browsers can do, and as a result, what information they might be able to leak about a particular user. And so what ends up happening is that in practice, like with many things involving browsers, there's sort of this living standard, right? So different browser vendors will implement different features, particularly with respect to private browsing. Other vendors will look and see what vendor X is doing. They will update their own browser, and so on and so forth. So it's kind of like a moving target. And as users grow to rely on private browsing more and more, they end up a lot of times actually finding bugs in private browsing mode, as I'll discuss a couple minutes later in the lecture. And so private browsing at a high level you can think of as sort of an aspirational goal, but we as society are sort of continually refining what it means to do private browsing and sort of getting better in some aspects, worse in some aspects, as we'll see a little bit later. So what exactly do we mean by private browsing? It's tough, but the paper tries to formalize it in two specific ways. So first of all, the paper talks about a local attacker on private web browsing. This is someone who's going to possess your machine after you've finished a private browsing session and then wants to figure out what sites you looked at in private browsing mode. And then the paper also talks about a web attacker. So the web attacker is someone who controls the websites that you visit. And this web attacker might want to try to figure out that you are some particular person, John or Jane, as opposed to some amorphous user that the website can't tell who they are. And so we'll look at each one of these attacks sort of in detail. But for now, suffice it to say that if the attacker can launch both of these attacks, both a local and a web attack, that actually really strengthens their ability to try to de-anonymize you. So for example, a local attacker who, for example, maybe knows your IP address can actually talk to the website and say, hey, have you seen this particular IP address in your logs? If so, aha, you're looking at the user whose machine I control right now. So it's actually pretty useful from the security perspective to consider these local and web attacks sort of as separate things and then to see how they can possibly compose. So let's look at this first type of attacker, which is the local attacker. So as I mentioned, we assume that this attacker is going to control the user's machine post-session. And so by post-session, I mean that the private browsing activity has already finished. The user's perhaps gone off, done something else, is not at the computer, and then the attacker takes control of that machine and wants to figure out what's going on. And so the security goal is that, well, we don't want the attacker to be able to figure out any of the websites that the user visited during this private browsing activity. Now, the reason why the post is actually important there is because if we assume that the attacker can control the machine before the user does private browsing, then basically it's game over, right? Because the attacker could install a keystroke logger, the attacker could subvert the binary that implements the browser, the attacker could subvert the OS, so on and so forth. So we don't really care about this pre-session attacker. And also note that we're not trying to provide privacy for the user after the attacker has controlled the machine. Right? And that's for the same reason. Right? Once the attacker gets the machine, he or she can do the same things I just mentioned, keylogger, so on and so forth. So basically, once the user leaves the machine, we sort of don't assume any forward notions of privacy. So does that make sense? Pretty straightforward. And so you can imagine that another goal that you might want to try to satisfy here is you might want to try to hide from the attacker that the user was employing private browsing mode at all. Right? Now, the paper actually says that that's very difficult. This property is often called plausible deniability. So, your boss comes up to you after you do some private browsing and says, were you looking at mylittlepony.com? You say, no, I certainly wasn't, and I certainly wasn't using private browsing mode to hide the fact that I was looking at mylittlepony.com. So, as I said, the paper says this is difficult to provide, this property of plausible deniability. I'll give you some concrete reasons why this might be the case a little bit later on in the lecture. So that's basically an overview of the local attacker. So one question we might want to think about is what kinds of persistent client-side state can be leaked by a private browsing session. And by persistent, I just mean stuff that will end up getting stored on the local hard disk or local SSD or whatever. So what kinds of state might be leaked if we weren't careful when someone's doing this type of private browsing? So one thing you might be worried about is sort of JavaScript accessible state. So examples of this include things like cookies and DOM storage. Another thing you might be worried about, and this is what most people think about when they think about what they want to save from private browsing, is maybe the browser cache, right? So you don't want someone to look in your cache and figure out, here are some images or HTML files from websites you prefer people didn't know that you visited. Another important thing is your history of visited sites. Right, so many relationships have been broken when the significant other goes to the browser, starts typing something into the address bar, and all of a sudden auto-completes to something very embarrassing, right? So this is one thing that definitely you don't want to leak outside of a private browsing session. You can also think about configuration state for the browser. And so here you could think about things like client certificates. You could also think about stuff like bookmarks. Maybe if you logged into a particular site and the browser offers to store your password, it's another type of configuration state that you might not want leaking from private browsing mode. Downloaded files. As we'll discuss, this one's a little bit interesting because downloading a file actually requires explicit user action to download that file. So maybe we do actually want this stuff to leak outside of private browsing mode. Maybe if you download something in private browsing mode, it should actually be accessible when you open up the browser or use your machine after that session. So we'll talk about this a little bit in a second. And then finally, during private browsing mode, you might install new plugins or browser extensions. That's another type of state that you might imagine you don't want to leak outside of private browsing mode. So basically, current browsing modes typically try to prevent 1, 2, and 3 from leaking outside of private browser sessions, right? So there shouldn't be any cookies or DOM stores to get out of there. Anything you put in the cache during the private browsing session should be deleted, and you shouldn't have any history of the URLs that you visited. Typically, 4, 5, and 6 private browsing modes allow to leak outside of the session. And there's some good and some bad reasons why this might be the case. And as we'll discuss later, we'll see that if you allow anything to leak from the private browsing session, that actually radically increases sort of the threat surface of privacy leaks. So it becomes much more difficult to reason about what the security properties are for private browsing mode. So does that all make sense? Anyone have any questions? OK, it's pretty straightforward. So the next thing we're going to talk about very briefly is network activity during private browsing mode. And what's interesting about this is that even if we cover all this stuff, we don't allow private browsing mode to leak anything from there, the mere fact that you're issuing network packets can actually leave evidence of what you were doing, right? So imagine that when you want to go to foo.com, the website, right, your machine actually has to issue a DNS resolution request for foo.com, right? So even if you don't leave any of this type of persistent state up there, there may be records in your local DNS cache that you, in fact, tried to resolve the host name foo.com, right? So that's very interesting. So you can imagine that browsers could try to flush the DNS cache somehow after the private session was over. Now in practice, that's actually tricky to do because on many systems, you require administrator privileges to do that. So it's not clear if you want the browser running as root, because browsers, as we've seen, are kind of somewhat untrustworthy individuals. And also, too, a lot of DNS flush commands, they don't actually act per user, right? They just sort of flush the entire cache, which is typically not what you would want if you were implementing private browsing mode, right? You'd want to do some type of surgical thing, like I only want to get rid of foo.com and things that were visited during this private browsing session, but not delete other things. So in practice, that's kind of a tricky thing to handle. And another tricky thing to handle, which the paper mentions, are these things that I'll call RAM artifacts, right? And so the basic idea here is that during private browsing mode, that private browser has to be keeping some stuff in memory, right? And so even if the private browsing mode doesn't issue any sort of direct IOs to disk, reads or writes, the RAM that belongs to that private browsing tab can still be reflected into the page file, for example. It can still be reflected into the hibernation file, for example, if it's a laptop, right? And so if that state gets reflected into persistent storage, then what may end up happening is that after your private browsing session is over, the attacker can look in your page file, for example, and find, for example, JavaScript code that was reflected to disk, or find HTML that was reflected to disk, and so on and so forth. So we're going to have a little demonstration of how this might work. So if you see up here on the screen, I basically loaded up a private browsing tab. And so what I'm going to do is I'm going to go to some website. So this is for the PDOS group here at CSAIL. OK, so I've loaded up that page. And then what I'm going to do is use this fun command called gcore. So basically, I'm going to take a memory snapshot of this running page. OK? And so I will do the following magic. OK, so basically, there's going to be some work that my terminal is doing to generate that memory snapshot. And so this takes a little bit of time sometimes. OK. And so now, what's happening here? OK, so now we've basically generated the core file for that private browsing image. OK, so what we're going to do now is we're going to look inside of that image and see if we can find any mentions of PDOS. Right? And so what's interesting is that we see a ton of instances of the string PDOS in that memory image for the private browsing mode. Right? And so what this means, and so what's interesting is we actually see various prefixes for things. If we look up sort of further up, we can see things like there's full URLs here and things like this. You'll also find HTML code in there, so on and so forth. And so the point here is that if we found all this in the in-memory image of that page, then if any of those pages got put to disk in the page file, then the attacker could basically just run strings, just basically do what I just did over the page file, and try to find out what sites that you visited in private browsing mode. So does that make sense? Basically, the problem here is that private browsing modes don't try to obfuscate RAM, basically, or encrypt it in any way. Right? And that seems like a pretty fundamental thing, because at a certain point, the processor has to execute on clear text data. Right? And so this is actually a pretty big challenge. So does anyone have any questions about yeah?
Yeah, so one thing is like, I don't expect my browser to do that. Like one thing is that these browsers, the guarantees that they give you through this private browsing is that the example they give is if you're shopping for something, you know, you're late,
yeah.
Your friend can't go on your computer and see the thing.
Right.
So, can you talk a little about, you know, what guarantees they give and if they have to change anything as a consequence?
Yeah, it's very interesting. So, you know, one thing you can look at is when you open up a private browsing tab, typically there'll be a little blurb that says like, hey, welcome to incognito mode. Here's what we'll help you against. We won't help you if someone's like standing behind you like with the rubber hose about to beat you, right? And so the browser vendors themselves are a little bit sort of cagey about what guarantees they provide, right? And in fact, after the Snowden incident, a lot of the browsers actually changed that splash page, right? Because they wanted to actually make it clear that we're not actually protecting you in some strong way against like the NSA or something like that, right? So long story short, what guarantees are they providing you? In practice, they're providing that sort of weak thing that you mentioned there. It's like a layperson, right, who wanted to see what you were doing afterwards, couldn't sort of figure out what you were doing. And we're assuming that the layperson can't, run strings on the page file or things like that. Now, there's actually two problems, though. One problem is that, first of all, because browsers are so complicated, they often don't even protect against the layperson. So I can give you a personal example. So a lot of times, like, you see those ridiculous ads from Huffington Post, like, oh my gosh, it's like puppies trying to help smaller puppies trying to go downstairs or things like that, right? So because I'm weak, I will sometimes click on those things, right? But because I don't want people to know that, I'll sometimes do that in private browsing mode, right? So I'll right click, open up, right? And so what will happen sometimes is that sometimes I'll see those URLs will leak into my URL history for like my regular public mode browsing, right? Which is precisely what this stuff is designed not to do. Right? And so one problem is that sometimes these browsers don't even provide protection against a layperson attacker. The second thing is that I think there are actually a lot of people who would like for private browsing mode to provide something stronger, right? Particularly with the whole Snowden thing. I think there's a lot of people increasingly who would like private browsing mode to protect, for example, against these RAM artifact attacks, even though they may not be able to technically articulate that goal. Right? And so actually one of the things I've done while I've been here is actually do some research into stronger private browsing mode protections. So if you're interested, we can chat about that. After all, one thing to learn about all professors is that we will talk about our research endlessly. So if you want to talk about that for 3 hours, just send me a calendar request and we can do that. So anyway, so this is basically a demonstration. Oh, you had a question?
Yeah, just about the RAM.
Yeah.
So I'm not familiar how it works exactly. How come the browser can't, at the end of the session, just ask the OS to flush those parts of the RAM that it was using?
OK. So we're actually going to get to that topic in a couple minutes. But you're correct. At a high level, what you can imagine is that maybe the OS, when it, for example, killed a process, would actually go through all those memory pages and write zeros to all those pages, right? Or you could also imagine that maybe the browser tried to pin all of its pages in memory to prevent anything from ever getting flushed out at all, right? So there are some solutions that can do that. So hold on to that question for 1 second. OK, so this is basically an example of how data from RAM can leak onto disk through paging activity. But note that data lifetime is a bigger problem than just in the context of private browsing. You can imagine that any program that deals with, let's say, cryptographic keys or user passwords will have this problem, right? Anytime you type in your password to a program, the memory page which holds that password can always get reflected to disk. So let me show you another example of this. So let's say that we look at the following program, which is pretty simple. So it's called memclear. So you see here at the bottom in main, we're just going to read in some secret text file here. And then we're just going to sleep forever. So what does that read secret do? Basically, it just reads in some file. It's going to print out the contents of that file. And then it's actually going to clear out the buffer that was used to store that secret information, right? So getting back to your issue, so what if we imagine the browser, for example, would try to just memset to 0 all the secrets that it encountered when it did some private browsing? So if we look at the secret file, not very fun, just says, my secret's in a file. And then if we run this program in the background, so what did it do? So like I said, it just printed out, it read that file in, printed out the secret value, okay, cleared the memory buffer that it used to print that stuff out. Now it's just sort of sleeping in the background. So once again, if we use this fun gcore command, we can take a memory dump of the memclear program that's running in memory right now. OK, and then if we do, let's see, which one do we want to look at? So then if we look at, I think this guy's the one we want. And then we do for a grep for secret, right? So once again, we see that if we look in the RAM image of that running program, we found instances of both the file name that was read in and also some prefixes of the string contents of that file, right? Even though we wiped the buffer in the C program itself, right? So you might say, why did this happen? This seems very, very strange, right? And the reason is that if you think about the way that I/O works, it's like a layer type thing, right? So by the time that the contents of that file get to the program, it's already gone through, let's say, the kernel memory. It's already gone through maybe like the C standard library to do I/O, because that library does buffering and stuff like that. And so what ends up happening is that even if you sort of memset the application visible buffer, there are still instances of secret data lying in many different places throughout the system, right? And this is just looking at the user mode portion of this application, right? So there's probably still data sitting around in maybe like the kernel's I/O buffers or things like that. So getting back to your question, if you want to do what they call secure deallocation, you can't just rely on mechanisms at the application level, right? Because there may be other places where that data lives. And so what are some examples of other places where this data might live? So for example, it might live in process memory. So these are things like the heap and the stack, right? And so when we did that memset inside of memclear.c, we were basically trying to address this. But what we found out is that that is necessary but insufficient to actually clear all instances of that secret from memory, right? So where else might RAM artifacts live or secret data persist? So all kinds of files, backups, SQLite databases, so on and so forth. If at any point an application takes something in RAM and writes it to one of these things, then once again the attacker may be able to recover that after the attacker controls the disk. As I mentioned, a kernel memory is another common place where RAM secrets may live. Because once again, applications typically do layered I/O in which each piece of data goes through multiple parts of the stack, right? Think of like a network transmission, for example, right? First, the data has to come to some network buffer that's probably inside the kernel. Then once again, it probably goes through some buffers inside of the C standard library. And then finally, it will go to the user mode, the part of the application the developer wrote him or herself. So that can actually be a big problem. You can also think, too, of freed memory pages as being a place where data can leak, right? So imagine that your application allocates a bunch of memory using whatever malloc or whatnot, and then that process dies, and the kernel spins up another process, but hasn't actually zeroed out all of the physical RAM pages, right? So what could happen is that when that new process spins up, it could just do a walk through all of its physical RAM pages. It could just allocate a bunch of memory, and just do the same thing, do the strings thing, see if there's anything interesting there, and then they might be able to get secrets that way, right? So there's actually a lot of ways that information can leak from the kernel. You could also think about I/O buffers from things like the keyboard, from things like the mouse. There's just a bunch of different vectors that data can sort of leak through the kernel. And so, how might an attacker try to get some of this information? Well, in some cases, it's just as simple as reading the files, right? So just read the page file, just read the hibernation file, and just see what's in there. Some file formats actually embed different versions within themselves, right? So for example, the way that Microsoft Word used to work is that a single Word file would actually contain versions for old pieces of data. So if you could somehow get access to that Word file, you could just sit there if you knew the format and sort of step through all the old versions. And so as we've been discussing in the last couple of minutes, secure deallocation is also a problem if it's not supported sort of full stack. So for example, in older Linux kernels, when you would create a new directory, you could leak up to 4 kilobytes of kernel memory. And only Zeus knows what's inside that memory. Once again, that's because Linux wasn't actually zeroing out kernel memory that had been allocated, deallocated, and then allocated to something else. And so, as I mentioned before, too, if the kernel doesn't sort of zero out pages that are given to user mode processes, you can also have user mode secrets leak through those types of memory pages as well. Another interesting thing is that so SSDs, many of them implement logging. And so, in other words, when you send a write to an SSD, oftentimes you're not directly overwriting data. You're actually sort of writing to a log, and when a piece of data becomes invalid, it's lazily reclaimed, right? And so what that means is that if you as the user get unlucky and you've written a bunch of data that hasn't been sort of reclaimed by the SSD, then maybe the attacker can sort of look at that hardware and just sort of say, ah, okay, I understand the log format. And even though technically speaking this data may be invalid, I can still recover it because I understand how the flash translation layer works or something like that. And at a high level, you can also have this problem with stolen or discarded hard disks as well. So if you don't use encryption, then a lot of times you can just sort of take some disk that you found in the dumpster somewhere, you understand what the physical layout is, and just recover data like that. So anyways, so there's a lot of problems with sort of these RAM artifacts getting stuck in persistent storage somehow, and then being available for an attacker later on. So how can we, so how do we fix these data lifetime problems? So we've already discussed one solution, which is to basically zero out memory when you're done with it. Right? So whenever you deallocate something, you just go through and you write a bunch of zeros or some random thing, and essentially hide the old data from someone else who might come along later. So does anyone see any potential problem with that? So one problem you might imagine is that, as with all things in security, people always complain about performance, right? And so when you say that zero out memory, maybe this isn't a problem if your program is I/O bound, so you're waiting on some slow mechanical part of the hard disk or whatnot. But imagine if your program is CPU bound, and maybe it's very memory intensive too, so it's always allocating and deallocating data. So maybe zeroing out memory might be a performance cost that you don't want to pay. Right? Typically, this isn't a problem in practice, but as we all know, people love performance. This is sometimes an objection that you'll have to this approach. Another thing you can imagine doing is that instead of zeroing out memory, you always sort of encrypt data as it goes to stable storage. Right? So in a system like this, basically, before the application ever writes anything to disk, it's actually going to encrypt it before it actually hits that SSD or that hard disk. Similarly, when that data comes back in from stable storage, you're going to decrypt it dynamically before you put it into RAM, right? And so what's interesting about this approach is that if the key that you use to decrypt and encrypt data, if you throw it away, right, then once you throw it away, you've effectively made that data on disk sort of unrecoverable by the attacker, right? Assuming that you believe in cryptography, right? And so this is very, very nice because it's sort of, it gives us this nice property that we don't have to remember, per se, all the places where we've written this encrypted data. We can just say, well, I've dropped the keys. And I'll just treat all that encrypted data as it's something that I could allocate again. And so, for example, if you look at OpenBSD, they have this option where you can do swap encryption. So you can basically associate keys with various sections of the page file. And so it does this very thing I mentioned. So every time you boot the machine, it'll generate a bunch of new keys, right? And then when your machine goes down because you shut it down or you reboot it or whatever, it'll basically forget all of the keys that it used to encrypt that swap space. And then it can basically say, OK, now all that swap is available to be used again. And so because those keys are forgotten, one can assume that the attacker can't look at the stuff that's in there.
So how does it derive the keys? Can an attacker predict the keys?
Yeah, that's a good question. So I'm actually not sure what sources of entropy it uses. So OpenBSD is pretty paranoid about security. So I'm imagining it does things like it looks, let's say, the entropy pool gathered from user keyboard input, for example, and other things like that. But yeah, I'm not actually sure how it derives those keys. But you're exactly right that if if the sources of entropy that it uses are predictable, then that basically shrinks the entropy space of the key itself, which then makes the scheme more vulnerable.
So the memory is trusted in this case. The attacker cannot read the memory.
The memory is trusted. Well, yeah. So basically what this model assumes, if all we're doing is restricting ourselves to looking at the swap encryption, right, it assumes that the RAM pages for the keys, for example, are never swapped out, right? And that's actually pretty easy to do if you're the OS, right? Because you can just pin that page in memory, right? And this also doesn't help you, someone who's like, got pins in the memory bus, or someone who can sort of walk the kernel memory pages or stuff like that. So you're right.
In terms of browsing, though, it kind of helps against attackers to come after the fact. Because if you throw away the key, then after the fact there is no key.
That's exactly right. That's exactly right. And so what's nice about this is that it essentially doesn't require modifications to applications. So like you said, you can just put any old thing atop this and sort of get this property for free.
Going back a bit, if you encrypt the data before the stable storage plane, decrypt it when it goes back to RAM, how does that avoid the RAM artifacts problem of just sitting there decrypted?
Okay. So if I understand your question correctly, I think you're worried about the fact that sure, data is encrypted when it's on disk, but then it actually has to sit in clear text form somehow in the actual memory itself. Right. So this kind of gets back to the discussion that we had here. So ensuring that data hits the disk encrypted doesn't actually protect against an attacker who can look at RAM in real time. Right. And so basically what we're saying is that if you're only worried about this post-session attacker who can't, for example, look at your RAM usage in real time, this works fine. But you're exactly right that this does not provide, for lack of a better term, like encrypted RAM. And there actually are some research systems that try to do something like that. It gets a little bit tricky because at some point, when you look at your hardware, your processor, it has to actually do something on real data. Right? Like, if you want to do an ad, like you have to pass it clear text, operands, perhaps. Right? There are also some sort of interesting research systems which actually try to do computation on encrypted data. This is kind of mind-blowing, like the Matrix. But suffice it to say that protections that people have for in-RAM data are typically much weaker than what they have for data that lives on stable storage. You had a question?
Yeah, but is that really realistic? Because even though the attacker has post-session access, that's just post-private mode access, right? So there could be still a public mode session going on, and the attacker would have access to the machine, right?
Let's see. So you're worried about a concurrent... Yeah, it's interesting. So we will talk at the end of the lecture about an attack which is somewhat similar, right? So most of the threat models for private browsing do not assume a concurrent attacker at all. So in other words, they assume that when you're doing private browsing, there is no other person who sort of has like a public mode tab open or anything like that, right? But you are in fact correct that the way that private browsing modes are often implemented, let's say you open up a private browsing tab, you close that tab, you immediately go run to get a cup of coffee, right? So one attack that I'll describe is that Firefox, for example, still keeps statistics about, let's say, memory allocation, right? And so if the memory for your private tab is actually lazily garbage collected, then I can basically go to like about.memory or whatever and actually see URLs and stuff in your tab. But long story short, most of these attacker models do not assume a concurrent attacker at the same time that you're privately browsing. Make sense? Okay. Yeah, so this is one thing you can do. Do swap encryption. Like I mentioned, this is nice because this gives you some pretty cool security properties without having to change the browser at all, or any applications running on top of it. And in practice, the CPU cost of doing this kind of thing is much, much lower than the actual cost of doing I/O in general. Right, particularly if you have a disk, right? Because with disk, you're typically paying seat costs. That's a mechanical cost. This is all sort of like processing costs, pure computational stuff. So typically, this is not that big of a performance hit. All right. Oh God, there's physics here. OK. So this is always an adventure. All right. So the next attacker that we're going to look at is this web attacker that I mentioned at the beginning of lecture. So the assumptions here are that the attacker controls the website that the user is going to visit in private browsing mode. However, the attacker does not control the user's local machine. And so the security goals that we want to have against the web attacker are twofold. So first, we don't want the attacker to be able to identify the user. And by identify, we just mean we don't want the attacker to be able to distinguish the user from any other user that happens to be visiting the site. And you also might imagine that perhaps we don't want the attacker to tell whether or not we're using private browsing mode. So attacker can't tell if user employs private browsing. And so as the paper discusses, defending against the web attacker is actually pretty tricky, right? So what does it mean, for example, to identify a particular user? Like I said, at a high level, you can imagine that the user looks no different than any other user that visits the site. So you can imagine the web attacker might want to do one of two specific things. It might want to say, OK, I've seen multiple people who are visiting my site in private browsing mode. You were visitor 5, 7, and 8. So in other words, identifying a particular user within the context of multiple private browsing sessions. The second thing that the attacker might want to do is actually try to link a user across public and private mode browsing sessions. So I go to Amazon.com once in public browsing mode. I then go to it again in private browsing mode. Can the attacker figure out that I'm actually the same person who did those two visits? Yes?
This is all the modulo of the IP address, right?
Yes, that's exactly right. So that is an excellent foreshadowing. So right now, I'm assuming that either the user employs Tor or does something like this. So yeah, we're just punting on this whole issue of IP anonymity for now. That's right. And so this segs very well. So what's an easy way to identify the user? As he just suggested, the IP address, right? So with pretty high likelihood, if you see two visits that are sort of close in time, relatively speaking, from the same IP, with high likelihood, that's probably the same user, right? And this is, in fact, sort of one of the motivations for stuff like Tor. And so we're actually going to discuss Tor next lecture. So in case you haven't heard of Tor, it's basically a tool which tries to obscure things like your IP address, right? And you could actually imagine layering Tor, having Tor be sort of the foundation, and then you put private browsing modes atop that, and that might give you some stronger properties than you would have if you just use private browsing modes at all. But anyways, so the thing to mention about Tor, though, is that Tor, it does provide some sense of IP anonymity, but it doesn't actually address things like the data secrecy lifetime issues or things like that. So Tor, perhaps you can think of it as like maybe necessary but insufficient for a full implementation of private browsing mode. And so what's interesting, too, is that even if a user employs Tor, there are still ways that a web server can identify the user by looking at the unique characteristics of that user's browser. And so this is our final demo for today. So let's see here. So we're going to get rid of this guy. And then, let's see, we're going to go to this site called Panopticlick. Okay? So I don't know if you've heard of this. It's run by the EFF. So the basic idea is that it is going to try to identify you, the user, by looking at various characteristics of your web browser. So I'll show you exactly what I mean. So we're going to go. This URL is very long, so this is very stressful for me to type in, so please don't judge if it doesn't go through. Let's see, Panopticlick. Yeah, looks good. Did it work? Yes. OK. So you go to this website, and it's run by the friendly folks at EFF. I say, OK, test me. So what this is doing is it's basically running a bunch of JavaScript code, maybe an applet, maybe some Java, and it's trying to fingerprint my browser. And it's trying to figure out, how much unique information does it have. And so let's see here. Let me increase the font here. So for example, one thing it looks at is it looks at, you see here, what are all the details of the browser plugins that I'm running? Okay, so basically it'll run code in this web page that looks and sees, do I have Flash installed? What version of Flash? Do I have Java installed? What version of Java? So on and so forth. And so you can see that, these are all, it can't even fit on the screen at one time. These are like all the various sort of plugins and ridiculous sort of formats that my browser supports. Now at a high level, this should probably be troubling to you if you're a security person, right? Am I actually actively using all of these things at any given time? This sort of gives me nightmares. But so what ends up happening is that web servers, this web attacker, they can run code like this, right? And they can figure out what are all the plugins that you're looking at. Now, if you look at these two columns to the left, what are they? So if you see up here, it says bits of identifying information, and then 1 in X browsers has this value. So for example, if we look at these plugins, it's saying there's basically, probably this is the number that's more interesting, right? This number on the right. It's saying that 1 in approximately 280,000 browsers has this exact set of plugins, right? So that's actually a pretty specific way to fingerprint me, right? It's saying that there's very, very few people who have this exact set of plugin configurations. So as it turns out, my parents were right. I am quite unique. But this is a problem from the security perspective, right? And so look at this. The screen size and the color depth for my machine. Right? 1 in, what is this? 1.5 million, right? So that's actually pretty shocking, right? So there's only one person, if you take a sample of 1.5 million people who would have this particular screenshot, this screen dimensions. And so note that these things they're additive in some sense, right? So it's like the more fingerprints you have, the more easy it is for the attacker to figure out exactly who you are. And so note, this was done purely from the server side. Right? I just went to this web page and I just did this, and then this is what it got to. 1 second, let me just show one more thing. So this was done in private browsing mode. And let's see here. If I just open up a regular version of Firefox, and then I run this stuff again. So note that now I'm in a public mode browser, okay? So before I was in private mode, now I'm in public mode browsing, right? And so what you'll see is that, for example, if we look at the browser plugins, like the extent to which I can be fingerprinted is essentially the same, right? There's going to be, a few plugins that may or may not load depending on sort of the vagaries of how privacy mode is implemented. But still, look at that. I'm still very easy to fingerprint. And in fact, if you look back at this guy again, that screen size and color depth, I didn't change that actually between the two, between public and private browsing modes. So that ability to fingerprint me there is basically the same. So this is one reason why it's so difficult to protect yourself against this web attacker, right? Because browsers themselves reveal so much information about you just through their configuration.
I'm just curious about the screen size and color depth thing. How does it do that? How is it that unique? How many screen sizes and color depths are there?
Well, so I think it's actually hiding some of the magic that it's using to figure out what that is. So at a high level, how do a lot of these tests work? So there's some parts of your JavaScript, some parts of your browser environment that are testable purely by JavaScript code. So you can imagine that you can essentially have JavaScript code which looks over the properties of the window object, which is like the global JavaScript namespace, and sees have you defined this weird widget? Have you defined this weird widget? And if so, that might count towards your plugins, let's say. Pages like this also typically take advantage of the fact that Java applets and Flash objects can look at all kinds of more interesting stuff, like the fonts that are available on your machine and things like that. So with respect to the particular screen size and color depth thing, I think, so don't quote me on that, but I think what ends up happening is that they'll try to run an applet, let's say. They'll actually try to query your graphics card or whatever sort of the graphics interface is in Java and sort of poke for different aspects of it. So I think it's actually more than just screen size and depth, but they kind of condense it for size as that. But at a high level, that's sort of how all these tricks work, right? So you see how much information you can sort of snarf up through JavaScript. Then you run a bunch of plugins, which can typically access more stuff, and then see what they can snarf up. And then you see what's going on. So does that all make sense? Yeah, so this is basically why it's very difficult to protect against the web attacker, right? And in particular, getting back to the discussion we had about Tor, right? Even if I'd gone through Tor, right? So you'll note that like IP address, you don't see it up here, right? And so you can imagine that, yeah, maybe this thing would actually look at your IP address. But the thing is, like, even if I didn't know what IP you were coming from at all, I can still do all these kinds of things, right? It's pretty madness. It's pretty insane, right? And so there's some products out there that try to do things like, imagine that you had a proxy out in the cloud that all your web traffic went through, and then imagine that proxy tried to present like sort of like a canonical version of a browser runtime, right? So imagine that it would always try to emulate, let's say, I don't know, Firefox v10.7, right? And then it would try to sort of send back the data that it rendered as Firefox v10.7. So there's some people who've tried to attack this, but it's very tricky.
How about Unix, WHONIX?
How about, I'm not familiar. Okay.
It's a pair of virtual machines. One of them is an install, the other one is the proxy.
I see. So the basic idea, I mean, is it a similar idea to what we were just talking about, such that, okay. Yeah, so I haven't heard of that one. I have heard of some of these other projects. I'm imagining, there's actually some trickiness in getting systems like this to be efficient a lot of times, because particularly imagine if you have something that's interactive, right? It's like you want to play a game or something like that. It's a little bit awkward to, send my mouse click to some proxy. That proxy is then somehow going to, send the,
I'd like to clarify that workstation virtual machine actually runs a canonical copy of Firefox.
Hmm?
And the proxy is only the Tor proxy.
Ah, it's just a Tor proxy. Ah, OK. So if it's just a Tor proxy, sure, that's one thing. Then basically the only overhead there you have to pay is sort of the regular Tor overhead of going through all the onion routes, right? Yeah, so what I was talking about is that there are some systems, let's ignore the IP anonymity for a second, that they basically try to say, you have your own very fingerprintable browser on your own machine. We don't want to expose that to the web server. So essentially, you go through a proxy, which think of it as almost having like a headless Firefox, let's say, of some canonical version. The web server thinks it's interacting with this thing. And so if I go load the site, I'm perceived by the web server as Firefox 10.7 or whatever. If you go there, you're also perceived as Firefox 10.7. But then behind the scenes, it's sort of spitting out HTML and stuff like that it collected from the proxy. So in a certain sense, those two things are orthogonal.
But it seems like you don't need a proxy for this. You could have browser support for this, right? The Tor browser kind of does this already.
So
trying to appear as the most generic version of Firefox.
Yeah, so this is true, although I think the problem with a lot of those things is that even if you try to sort of lock yourself into one version, there's still a lot of things that can be fingerprinted. So I think with the Tor distribution, what they often do is they say, like, we control what's in the Tor distribution, right? So if we all go and download the Tor distribution, then for shizzle, we're both going to get Firefox with the same Java version and the same so on and so forth, right?
It's more than that, though. Like, they return screen sizes that are the most common screen sizes whenever you query for query.
Yeah, that's all true. Yeah, so one thing that's interesting to look at, though, is so the Tor team, they'll often put out, or the people who do the bundle, they often put out like these reports about what data still gets leaked. So stuff does still sometimes get leaked out of that. But you're right that if you could, I mean, at a high level, that goal is very reasonable. It's saying that if we all agree to download the same distribution and to then not trick it out by adding plugins or stuff like that, then you're exactly right. That'd work great. Any other questions? OK. So yeah, so that is it for demo time. Let's turn that guy off. And there's more physics. All right. Must have been a riveting previous class. So we will ignore that for the moment. Let's see here. All right. So where were we? OK. So as I was talking about, what is the high-level goal of privacy? And you can think of it as what's your anonymity set if you're a user. So in other words, what's the size of people, the number of people that sort of you could be confused for, you could be mistaken for by an attacker. And so what the browser fingerprinting stuff shows is that oftentimes a web attacker can sort of narrow you down to a very, very tight demographic, right, without controlling anything on your local machine whatsoever. And so that's actually sort of a little bit frightening to know. All right, and so you might want to think about how can a web attacker determine if you're using private browsing mode. Maybe that's useful to the attacker for some reason. So in the paper, they actually describe an attack that uses link colors. So if you remember, in private browsing mode, the browser isn't supposed to keep track of the history of the sites that you visit. And so in the paper, the authors describe an attack in which essentially the attacker-controlled page creates an iframe, right, to some URL that the attacker controls, and loads that inside the attacker page. And then it basically looks at the link color. It creates a link to that page, that iframe that it just created, and then sees that the link color for that link is the visited color. So sees if it's purple versus if it's blue, right? And the idea is that if you do this test in private browsing mode, then presumably the link color should stay like the unvisited color, right? Because the browser is supposed to be forgetting about all this kind of stuff, right? And so that's the attack that they describe in the paper. What's interesting is that this attack actually doesn't work anymore, right? So we actually discussed this a couple lectures back, right? So this attack that the paper describes is the browser history sniffing attack, right? And so as we discussed a couple lectures ago, JavaScript code now does not expose correct link colors, basically, to JavaScript. And the reason is precisely to prevent these types of attacks. So that particular part of the paper is a little bit outdated. But you get, go ahead.
Just a point to that browsers now also show links as purple in private browsing mode.
Yes.
And then
yes.
turn blue again when you exit.
Yeah, it's a bit weird. Yeah. So they implemented that attack, the defense. Yeah, I think before a lot of the private browsing mode stuff got popular. So now they do this additional thing too. But long story short, the attack they describe in the paper doesn't work because of some of these browser sniffing defenses. But you can still imagine that there may be ways for the web attacker to figure out if you're using private browsing mode. So for example, when you do private browsing mode, any cookies that you got from public mode should not be sent during private mode, right? So in other words, if I go to Amazon.com in public mode, I generate some cookies, right? Then I go to Amazon.com in private browsing mode. When I contact Amazon.com in private mode, those public mode cookies should not be sent, right? But that can actually act as a sign to the web attacker that you actually are using private mode.
This is also, now you're using the IP address in both of these attacks, right?
Yeah, so that's right. So
the link that you were targeting with the link color, it would be on a per IP basis. And you would have to rely that the user first visited it in public mode and you detect it.
so the link, so the link attack you can actually do in the context of a single page, right? So imagine that I, the web attacker, can construct a single page, right? I, the attacker, have JavaScript that creates an iframe to foo.com, let's say, right? So that iframe will just load in the context of that page. And then I, the attacker, in the parent frame can then create a link element and then try to look at the color. I mean, this worked 4 years ago, right? So in that case, it doesn't rely on the user having explicitly visited that iframe page at all. Because I, the attacker, can just create that in the context of the page I have gotten the user to visit. Any other questions? OK, so yeah, so you can maybe think about how cookies can reveal public or private browsing modes and things like that. All right, so one thing we might think about is how can we provide a stronger privacy guarantees for private browsing. And for the sake of this discussion, let's just ignore IP addresses for now. Because as we'll discuss next lecture, we can use Tor to maybe help with some of the privacy of IP addresses. So one thing you can imagine doing is you can imagine using VMs in some way to help provide stronger private browsing guarantees. So VM level privacy. And so the basic idea is that you want to run each private session inside of a separate VM. And then when the user is done with that, so is finished with the private browsing session, you basically delete VM after that session is done. Right? And so what's the advantage of this? Well, what's nice about this is that presumably you can get some stronger guarantees about what privacy properties you can provide to the user. Because presumably, the VM has a pretty clean interface to the I/O path of the underlying sort of host OS. So you can imagine that maybe you combine this VMs with maybe, let's say, some type of secure swap solution like OpenBSD has, some type of encrypted disk type thing. And so you can imagine, okay, we have a very clean separation of, sort of the VM up here and all the IOs that it's generating down here. And so that gives you sort of stronger guarantees than what you can get from the browser, which wasn't sort of designed from the ground up to sort of think very carefully about all its I/O paths and what secrets might leak to persistent storage and so on and so forth. So this provides sort of what's nice about this. So strong guarantees. And also what's nice is it doesn't require any changes to your applications. That is to say, to the browser, right? You just take your browser, put it inside one of these VMs, right, and then everything sort of gets better automatically, right? So no application changes. So what's bad about this? Use an unhappy face to demonstrate that. So what's bad is, first of all, it's heavyweight. And by heavyweight, I mean that every time you want to spin up one of these private browsing sessions, you have to spin up a whole VM, right? And that can actually be pretty painful. Right? So perhaps users are going to get upset because it's going to take them a long time now to launch these private browsing sessions. And the other problem, too, is this solution actually has bad usability. And the reason I say that is because now it's actually difficult for users to do things like take files that they've saved in private browsing mode and then take them to the rest of their computer, any bookmarks that they generate during private browsing mode that they actually do want to persist. It'll be difficult to sort of get those out of the VM. It can be done, but there's a lot of friction here. So that's kind of a bummer. So another thing that you might imagine doing is something that looks kind of like approach number one, but we actually implement this inside of the OS itself instead of in a virtual machine. So the basic idea here is that you can imagine that each process could potentially run in a privacy domain. Right? And so basically the privacy domain sort of acts as sort of the collection of OS level resources that process uses. And so the OS tracks all that kind of stuff. And then once the process dies, essentially the OS goes through, looks at all the things that are in that privacy domain set, and then securely deallocates all of those resources. And so the advantage of this over the VM is that it is lighter weight. Right? Because if you think about it, the VM is essentially agnostic to all of the OS state and all the application state that it is actually being used to run. Right? So as a result, it probably does more work than the OS would have to do. Because the OS presumably knows all the points at which the private browser would be touching I/O and talking to the network and stuff like that. And so maybe it even knows things like it can actually clear the DNS cache selectively, for example. Right? And so you can imagine that it's much easier to spin these things up, these privacy domains, than to tear them down. However, the sad thing, at least with respect to the virtual machine solution, is that it's harder to get this right. So, I just finished describing the VM approach as being heavyweight because it's essentially agnostic to everything that's running sort of inside the container. But what's nice about that is that that allows the VM approach to only focus on a few low-level interfaces. And if it can focus on those things, like for example, the interface the VM uses to write to disk, then it can have high probability, high confidence that it's actually managed to contain everything. Whereas with the OS, right, if you think of the OS as going to interpose on individual file system interfaces, perhaps individual network interfaces, stuff like that, it's much more complicated to find all of those points at which data can leak if you're going to do that at the OS level. So does that all make sense? OK, so let's see here. Move this guy up. Why is there physics everywhere? God, being tested. Okay. So, those are basically some approaches that we can use to provide potentially stronger privacy guarantees than what's implemented in private browsers right now. So, one question you might have is, so can we still de-anonymize the user if the if the user is employing one of these more powerful solutions, right? If the user is surfing through a VM or surfing through one of these privacy domains in the OS, can we still figure out who they are? And yeah, the answer is yes. So, maybe the VM is unique for some reason. And so similar to how we were able to fingerprint browsers using that panopticlick site, maybe there's something unique about the way that the VM would be set up that will allow us to fingerprint it, right? And it may in fact be the case that maybe the virtual machine monitor or the OS itself is unique in some way that would allow a web attacker to figure out who the user was. And so one sort of cute example of this is TCP fingerprinting. So what's the basic idea behind this? So as it turns out, the specification for the TCP protocol actually allows some of the parameters for the protocol to be set by the implementation of the protocol, right? So for example, TCP allows implementers to choose things like the initial packet size for the thing that gets sent out, the first part of the TCP connection. It allows implementers to choose things like that initial time to live in those packets, so on and so forth. And so you can imagine, and in fact you don't have to imagine, this is actually the truth, you can get off-the-shelf tools like Nmap, for example, that they actually can tell what operating system you're running with high probability just by sending you packets. Right? They'll send you these very carefully crafted packets. Then they'll look and see things like, here's what the TTL was, or here's what the packet size distribution was, here's what the TCP sequence number was. And they basically have a database of fingerprints. Right? And they say, OK, if the return packet has this, this, and this characteristics, then the table says that you're probably running, for some reason, Solaris, right? Or you're running Mac, you're running Windows, or whatever. Right? And so even if we use one of these stronger approaches for private browsing that leverages a VM or an OS, you still may be able to run one of those TCP fingerprinting attacks and learn a lot about a particular user. And one thing that's also sort of interesting to note is that even if we use one of these more powerful techniques to try to protect the user is still shared across both the public and the private browsing session. Right? It's still you who's physically using the machine. So why is this interesting? Well, it's interesting because you yourself, just by dint of the way that you use computers, may leak information about yourself. So for example, as it turns out, users have unique keystroke timings. Right? So if I look at it, if I give everyone in this class sort of the same thing to type in, the quick brown fox, whatever that nonsense is, right, and I actually look at the inter-key press timings, right, we'll all have these unique distributions, right, that can potentially be used to fingerprint us. Another thing that's interesting is users have unique writing styles. So there's this branch of security that is called stylography. And the basic idea here is to figure out, if I'm an attacker, can I figure out who you are just by looking at writing samples from you? So imagine that for whatever reason you're hanging out on 4chan. Don't hang out on 4chan. And I want to figure out if you've actually, in fact, been hanging out on 4chan. So perhaps what I can do is I can look at a bunch of different posts from 4chan. Maybe I can cluster those posts into like sets of posts that I think look stylistically the same, right? And then what I can do is I can find things that you've written publicly where you're actually attributed as the author. I'll look at your homework assignments or your papers that you've written or things like that. Then I'll see, do you map to any of these clusters from these 4chan comments? And if so, then maybe I can say like, send you a stern note, talk to your parents like your kid's gone off the beaten path, get off of 4chan, right? So if you're interested in this, like I said, look at this thing called a stylography. It's actually quite interesting. Does anyone have any questions about that? Excellent. Okay. So we've discussed how we might be able to use VMs or sort of modified operating systems to provide private browsing support. And so you might wonder, okay, well then why don't browsers just sort of require users to do one of these things, to have one of these tricked out VMs or tricked out OSs? So why do browsers take it upon themselves to implement all of this stuff? And so the main reason is deployability, right? So in fact, browser vendors typically do not want to ask their users to do anything special to use the browser besides just install the browser binary itself. This is sort of similar to the motivation for native clients. So Google wants to add this kind of cool feature to end users' computers, but it doesn't want to force users to install some special version of Windows or Linux or whatever. So Google basically says, we'll take care of this ourselves. And then another reason is actually usability. So a lot of these VM and OS level solutions for private browsing, as we've discussed, they make it more difficult for users to sort of persist state from private browsing sessions that they do actually want to persist, right? Like downloaded files, like bookmarks they create and things like that. And so basically the browser vendors say, well, if we implement private browsing modes ourselves, we can actually allow users to do those things. We can allow users to take downloaded files from private browsing mode and take them to the rest of the machine. So that seems kind of nice at first, but note that, of course, that allowing users to export some types of private state actually opens up a lot of security vulnerabilities, right? And it makes it very difficult to analyze the security properties that the resulting private browsing modes actually provide. And so in the paper, they try to characterize the different types of browser state that can be modified and how current private browsing modes actually handle the modification of that state. So the paper describes this taxonomy of browser state changes. And so there are 4 things in this taxonomy. So one type of state change is initiated by the website itself, and there's no user interaction. And so examples of this type of state change, think about stuff like when a cookie gets set, when something gets added to the address history of the browser, maybe when the browser cache gets updated. And so for this type of state, basically private browsing modes say that this stays within the private browsing mode session, but is basically going to be destroyed when that private browsing session concludes. Okay? And so the sort of intuition behind this is that because there's no user interaction in creating this state, then perhaps the right thing for the browser to do is assume that the user wouldn't want that stuff to persist. Right? So another type of browser state change is it's initiated by the website that the user is visiting, but there is some type of user interaction involved with the state change. So an example of this might be the user installs a client certificate, or maybe there's like a saved password. So the user tries to log into something, and the browser says very helpfully, would you like to save this password? And then if the user says yes, then these types of things like the save password can actually be used outside of the private browsing mode. And so it's a little bit unclear sort of in principle what the policy for this should be. So what ends up happening in practice is that browsers typically allow state that's in this category that's set in private browsing modes to persist outside of that private browsing mode, under the intuition that since the user did have to say yes or no, if the user said yes, then maybe the user's smart enough to understand that if they save some password for some unsavory site, and then someone comes on later and figures that out, that's the user's fault, not the browser's fault. So like I said, it's a little bit unclear what the best policy is here, but in practice, this type of state change is allowed to persist outside of private browsing mode. So there's another type of state change which is just purely initiated by the user. And so here you can think about things like setting a bookmark, or maybe downloading a file. And so the story for this state is similar to the story for the state up here. So basically, because the user was explicitly involved in the creation of that state, private browsing modes typically say, OK, so that's OK to persist these types of changes to sort of the outside world, outside of the private browsing mode. And there's some sets of state which are actually unrelated to any particular session at all. So this is stuff, for example, like an update to the browser itself, the actual binaries that constitute the browser. And so the way that browser vendors think about this state is that this state is essentially assumed to be sort of part of a single global state that's available to both public and private browsing modes, right? And so what's interesting is that if you look at this, there's actually quite a lot of state that will actually potentially leak outside of private browsing modes, particularly if there's user volition involved. And so it's interesting to think about, is this sort of the right trade-off between security and privacy? And so what's interesting is that, so the paper actually says that it's difficult to sort of prevent a local attacker from detecting whether or not you've been using private browsing mode. And the paper was a little bit vague about why this might be the case. So one reason why this might be the case is because some of this state that actually leaks from private browsing mode to public browsing mode intentionally, it can actually contain hints that the state was generated in private browsing mode. So for example, on Firefox and Chrome, when you generate a bookmark in private browsing mode, that bookmark has a bunch of metadata with it. So for example, the time that it was visited and things like that. So in many cases, that metadata will be set to 0 or to some null value if that bookmark was generated inside of a private browsing mode, right? So then later on, if someone controls your machine and can look at your bookmark information, if they see this metadata set to this 0 or null value, they can say, aha, that bookmark was probably generated in private browsing mode. So one thing to think about is, typically when we talk about browser security, we talk about, OK, what can people do with JavaScript or HTML or CSS? One thing you might want to think about as well, what can people do with plugins or extensions? So in the context of private browsing, plugins and extensions are quite interesting because they're not constrained in most cases by the same origin policy that constrains stuff like JavaScript. And what's interesting is that these extensions and plugins typically run with very high authority. Right? Loosely speaking, you can think of them as like kernel modules, right? They implement new features directly inside of the browser themselves. And so that's a little bit problematic because these plugins and extensions are often developed by someone who's not the actual browser vendor, right? And so what that means is that someone's trying to do something nice and provide you this nice value add in this browser plugin or extension, but that implementer might not fully understand the context, the security context in which that extension runs. So that extension may not implement private browsing mode semantics, or it may try to implement it but do it in a bad way. And so as I'll describe in a couple minutes, that's actually sort of bad from the security perspective, because that means that when you add some of these new plugins or extensions, you now can't strongly reason about what the resulting privacy semantics for the browser are. Now, one thing that's nice is that plugins are actually probably going the way of dinosaurs. So as you probably know, like HTML5 adds all these new features, like the audio tag and the video tag and stuff like that. And so a lot of these new features were designed to allow people to get away from plugins, to get away from Java, to get away from Flash. So when people in the past wanted to do things like have rich 2D or 3D graphics, they'd have to use something like Java or Flash. Now they can use things like WebGL, they can use things like the canvas tag, so on and so forth. So probably plugins are going away. And in fact, like IE team, for example, has said that in a couple years, they don't think anybody's going to be using plugins whatsoever. It's all going to be like HTML5 type stuff. And in fact, if you go to YouTube, I don't know if you've noticed, but a lot of times if you go to the video is actually using, it's called like the HTML5 player, right? They've gone away from sort of their standard plugin-based one, right? So that's very interesting. So you can already see sites trying to move towards this new plugin world. However, extensions are probably here to stay for at least the foreseeable future, so it's still important to get those right. So yeah, so the last thing that I want to discuss is, so that the paper was written in 2010, right? So that's 4 years ago. So you might think to yourself, well, what's changed about private browsing mode? And so at a high level, private browsing mode is still tricky to get right. And the reason why it's tricky to get right is a couple of reasons. So first of all, because the browser API is still growing, because of things like this HTML5 stuff, right? The interface, which needs to be secured with respect to private browsing mode, that frontier is always getting bigger, right? And also, a lot of times, developers, they're more focused on sort of adding cool new features, and then the privacy implications sort of get taken up later on. And so, in practice, it is still tricky to produce a private browsing mode which catches all potential data leaks. So one example, there was a Firefox bug fix from January 2014. And the basic idea is there is this extension. It's called PDF.js. It's basically a way to look at PDF files using pure HTML5 interfaces. And so as it turns out, this extension was allowing public mode cookies to leak when it was being used in private browsing mode, right? So the idea is that, let's say that you visit some website in public mode, you want to download some PDF, maybe you get some cookie that comes back. You come back in private browsing mode, you want to view another PDF from that site, and then PDF.js was actually sending those public mode cookies along with any private mode cookies that were set. And so in the lecture notes, I actually have a link to the the Bugzilla discussion about this particular bug. So the fix was actually quite simple once they realized this was a problem. They basically just have to add a check that says, morally speaking, am I in private browsing mode? If so, just do some things, and one of those things is not send the cookies. So the fix here was actually quite simple. But the challenge was that, once again, people had added this cool new extension, but it hadn't really crossed their mind to sort of do this sort of very sort of full invasive audit and say, where are all the places at which private browsing mode semantics might be impacted by this particular plugin. There's another interesting one too, gets back to a discussion we had about 30 minutes ago about what happens if you have sort of like private tabs and public tabs maybe open at the same time or very close to each other. So there's actually a bug in Firefox, I think it's from, let's see here, yeah, 2011, which is still unfilled. And the basic idea is that if you go to a tab in private browsing mode, okay, you go do some stuff, you then close that tab, okay, you then open a new public mode tab and you go to about memory. So as you probably know, browsers define these sort of fake URLs to tell you information about how the browser works. So you go to the private tab, close it up, then go to about memory. This is going to tell you information about all the objects that Firefox has allocated, right? And so what would happen is that window objects are typically deallocated. They're garbage collected lazily in Firefox. So what could end up happening is that when you open up that new public mode tab, go to about memory, you can actually find information still about that private mode window, right? Such as things like its URL, for example. It'll tell you how much memory was allocated and all that kind of stuff. And it's all in the plain text, right? And so that's an example of how there are these very subtle interfaces in the browser that can actually leak a lot of information. And so it was very interesting. So if you look at the Bugzilla discussion, it's actually pretty interesting to sort of see how these problems get resolved in real life. And I put a link in the lecture notes to it. So there's a message that says this bug was deprioritized when it became clear that the potential solution was more involved than originally anticipated. Right? So there's actually a pretty long discussion about how do we fix this. And it involved like changing the way that garbage collection is done, and like the garbage, it's very tricky because if you invoke it too often, maybe that's a performance hit and so on and so forth. So there's this long discussion about this. So they said it was deprioritized when it was clear the solution was more involved than anticipated. And then in response, a developer said, that is very sad to hear. This can pretty much defeat the purpose of things like Session Store forgetting about closed private windows. Right? So developers do care about this stuff. And like in the case of Session Store, this sort of storage feature for HTML5, they'd gone to a lot of trouble to make it delete things that belonged to these closed private windows. But basically what this bug did is it basically still left information about that stuff sitting around in memory somewhere. So long story short, it's still very difficult to get private browsing right. And in fact, there are actually off-the-shelf forensics tools that you can download that will actually look for evidence of both public and private browsing modes, right? So if you're an attacker, you don't have to roll your own custom tool. There's this one thing called like Magnet, I think it's Internet Evidence Finder, right? You just go get this thing. It'll do things like look through your page file for RAM artifacts, right? And it'll give you a very nice GUI. It'll say, here are the images I found, here are the URLs, so on and so forth. So in practice, these private browsing modes still do leak some information. All right, so next lecture we're going to talk about Tor. All right, see you then.